Hi everyone. This series of videos is intended to introduce the Analog Discovery Board and the Waveforms software. I'm Professor Ram from the Engineering Department at UMass Boston, and I also run the Ubiquitous Communications and Networking Lab, or UCAN Lab. In this video we will demonstrate analog signal generation using the Waveforms Wavegen tool and the AD2 board's waveform generator channels. As usual, I just want to note that you can find much more detail about these tools in the Digilent reference documentation at the link shown here. Looking at our AD2 pinout diagram, we can find two wires that we will be using in this video. Pins W1 and ground, which is indicated by the downward pointing arrow. W2 is the second Wavegen channel that we will observe in a future video. In our waveform software, we will be using the Wavegen tool. Once we open Wavegen, we will see a number of options to control a few pre-configured waveforms with parameters like frequency, amplitude, offset, and symmetry. In a later video, we'll also demonstrate how to create custom waveforms and synchronize the two waveform generator channels. We're going to demonstrate signal generation across an LED so that we can easily visualize what happens when we send some low frequency signals. We'll then demonstrate our need for an oscilloscope when the frequency of the signals goes beyond what we can comprehend visually. Let's begin by starting the Waveforms software and opening our Wavegen tool. We can see the signal properties in the top left and a visualization or preview of our signal to be generated in this main window. On our AD2 board, we have a simple setup with pin W1 connected to the anode of our LED and our ground pin connected to the cathode of our LED. Note that a diode ideally has a fixed voltage drop, so we would usually put the LED in series with a resistor, but the AD2 board does have some internal resistance, so we can actually attach the signal directly across the LED as we've done here. Coming back to waveforms, we're going to create a signal that turns the LED on and off. We can see that our amplitude is 1 volt by default, and accordingly our sine wave goes from -1 volt to 1 volt. Since we have a turn-on voltage of around 1.7 volts for our LED, we can set our offset to 1 volt. This helps us shift our signal up by 1 volt so that our new range is now from 0 to 2 volts. We can also change the type of our signal to a square wave so that our LED is either on or off. Lastly, we'll change the frequency to 1 Hertz so that we can actually visualize what's happening with our LED. When we do this, we see that the period automatically changes to 1 second, and our time axis shows that our signal is high for the first 0.5 seconds and off for the remainder of the period. When we select Run, we can now see our LED blinking. When we select Stop, the Wavegen holds the current voltage, so we might see that the LED remains on, although it's not in this case. We can play around with our amplitude and offset as they jointly determine the range of our signal over here. For example, if we change our amplitude to 500 millivolts and our offset to 3 volts, we can see that our range of our signal is now between 2.5 volts and 3.5 volts. In order to see the effect of the signal amplitude, let's add a 1 kilo ohm resistor in series with our LEDs so that the voltage drop has, or the voltage across this has a more observable impact on the LED's brightness. Keep in mind that the LED's voltage drop is essentially constant, so increasing the voltage of our waveform increases the voltage across the resistor, which then increases the current through the resistor in the LED. More current through the LED means more optical power and a brighter light. Now when we start our signal again, we can still see that the LED is blinking, but rather than turning on and off, we're seeing that it's always on and blinking between the two different brightness levels. If we change our waveform to a sine wave, we can see a smoother transition between the brightness levels. If we change this to a ramp up signal type, we see that the brightness slowly increases and then immediately drops back down. Changing our amplitude to 2 volts and keeping our offset at 3 volts, we see that our ramp actually goes from 1 volt to 5 volts. Keeping in mind that our LED's turn-on voltage is approximately 1.7 volts, we can see that the LED turns off and then the brightness slowly ramps up as the signal goes up to 5 volts. We can also try to keep the LED on with this same range by changing our offset to 4 volts so that our signal would range from 2 to 6 volts. But we can see in our signal preview that the ramp flattens out at 5 volts. This is because the AG2 has a peak voltage output of 5 volts. To demonstrate our change in frequency, we can go back to a square wave with a 2 volt amplitude and a 2 volt offset. If we change our frequency to 5 Hertz, the LED blinks faster as expected. We can also see that our horizontal axis in our signal preview automatically updates to a period of 200 milliseconds. If you continue to increase the frequency or decrease the period, you will notice that your eye can no longer perceive the difference around 60 Hertz. Similarly, the webcam cannot pick up these differences, but the LED is still capable of turning on and off much faster. The reality is that beyond a certain frequency, we're only perceiving the average brightness here. We can see this by modifying the symmetry parameter of our signal, which relates to the signal's duty cycle. If we update our frequency to 500 Hertz, we see that our new period of 2 milliseconds with 1 millisecond on and 1 millisecond off. Now if we change our symmetry to 10%, we see that the signal is on for the first 0.2 milliseconds and off for the remainder of the period. Observing our LED, we can see that the brightness decreased. If we change our symmetry now to 90%, the pulse is 1.8 milliseconds and off for only 0.2 milliseconds. So our average brightness is higher and we can see that the LED appears to be brighter. This concept is essentially how many dimmable LED lights work using pulse width modulation. Rather than changing the DC voltage, they keep a constant minimum and maximum voltage, but modify the pulse width or duty cycle in order to change the brightness of our lights. That's our basic introduction to the Waveforms Wavegen tool. In the next few videos, we will show how to create custom waveforms, use multiple waveform channels, and ultimately observe these higher frequency signals using the Waveforms scope tool.